Welcome to Module 7 of Statistical Analysis, Topic 7.3, Descriptive Statistics and Tables. By the end of Topic 3, you'll be able to understand and identify types of quantitative data and distinguish between types of continuous and categorical data, summarize categorical data with frequencies and relative frequencies, and numerical data by calculating and interpreting measures of central tendency and spread, create frequency tables, contingency tables, and other data summary tables, and use Stata to generate your summary data. If you want to follow along in Stata or perform these functions in Stata later, you can do so using the Mix 2017 10% random sample data file and the do file for Module 7, Topic 7.3. Descriptive statistics allow us to organize and summarize our data, which helps create a context for understanding our sample and population. We often use visual ways to organize and describe data, like tables and graphs. In this section, we'll talk about tables, and we'll take a deeper look at graphical representation of data in Topic 7.5. When we're storing data, we typically store our data in a table to organize it by observations, by rows, and variables in columns. We may also present and report data in a table format, similar to the way we store data. This is a simple table reporting characteristics of hepatitis A cases in a health department over the course of 2 months. Each row represents one case or observation of hepatitis A seen at this health department. The observation has an identifying number or ID first, and then across the row we have the values for each data point collected, such as date of diagnosis, age and sex of the person with hepatitis, and how it was treated. Rows often represent a person, an observation, a record, or a case of a disease. The vertical columns each represent one variable and each data point of that variable for every person or observation. In this case, I've highlighted the variable sex or gender at birth, and you can see that each row has an M for male or an F for female. A variable is essentially any characteristic that can be measured that varies or takes on different values for different members of the dataset, such as gender, age, weight, or blood measurements. In order to effectively present data, it is important to recognize different data types. Proper data summaries and analysis depend on data type as well. As we introduced in 7.2, there are two main data types, categorical and interval. The categorical data has two subtypes, nominal and ordinal. Interval data also have two subtypes, discrete and continuous. As you move from nominal to continuous data types, the amount of detail contained in your measurement increases. This flowchart from Topic 7.2 provides an excellent overview of the branches of each data type. We'll spend the next few slides going into greater detail about the distinguishing qualities of each type and subtype of data. Categorical data consists of nominal variables, which are unordered categories in which the ordering and magnitude are not meaningful. Examples include binary or dichotomous variables, such as gender at birth, the presence or absence of a disease, or responses to yes/no questions. Examples of variables with more than two categories are ethnicity, regions of a country, or lists of vitamin supplements. For all of these variables, the order doesn't matter, and none of the categories are greater or lesser than another. With ordinal variables, values fall into categories with some inherent order, So the order is important, but not the magnitude. You still don't have one value that is, for instance, twice as much as another. Categories might include ranked data, but the space between the categories is not important. Examples are measures of income or wealth, level of education, or the responses to Likert scale questions ranging from strongly disagree to strongly agree. Here we see example categories for indicating level of pain or how often someone feels depressed. Most arithmetic operations don't make sense with categorical data, so we use other types of operations to analyze this type of data. You may also hear these types of data described as scales of measurement. Nominal measurement classifies data into mutually exclusive or non-overlapping, exhaustive categories in which no order or ranking can be imposed on the data. A few examples here again are, in the past 12 months, have you or another family member living in your household missed any form of medical treatment due to the cost or not? With response options are dichotomous yes and no responses. Sex at birth also has dichotomous response options. And a question about province would theoretically provide a list of provinces to choose from. In the mixed data, a question about ethnic group of the head of household has these 5 categories of responses. You can see that for none of these questions does the order of responses matter, nor does any category have any value of magnitude. Ordinal measurement classifies data into categories that can be ordered or ranked, but are not necessarily evenly spaced. Examples here include ordered categories of frequency of exercise, self-rated general health, and in the image, the mixed data variable ED5 contains the responses to a question about the highest level and grade or year of school that a household member has ever attended. All of these response options contain an inherent order, but the difference between one unit and the next does not have a specific value. With interval data, arithmetic operations apply, and both the order and magnitude of the variable value are important. Discrete variables are typically ordered in numbers or counts, usually an integer. Discrete values can assume only a finite or countable number of values and are restricted to taking on only specified values that do differ by a fixed amount. Examples might be the number of cigarettes smoked in a day, the number of cases of a disease, or number of hospital visits in the past year. Continuous variables can take on any value between 2 specified values. It is not restricted to taking on the specific values, and the difference between any 2 possible data values can be arbitrarily small. Continuous data can assume the infinite values, so may have many decimal places. Examples include weight, height, age, or the blood levels of some nutrient you're measuring. Discrete measurement ranks data on a scale of equally spaced units, in which a given difference between scores has the same meaning anywhere on the scale. We typically think of these as counts, such as how many children under the age of 18 live in your home, or what is your youngest child's age in months, or the number of ear infections a child had before the age of 5 years. Continuous measurement also ranks data on a scale of equally spaced units, but there is no restriction on the values it can take. all of the decimal spaces between integers are possible in continuous measurement, as we see again in measures of weight, length, or height, or blood levels of hemoglobin. We can also manipulate continuous data to have less detail, such as how we transform BMI into BMI categories, or in the mixed data, indicate severe anemia. To review, if you can take a moment to think about what level of measurement would be used for each of the images here. Sex or gender at birth, length in centimeters, the winners in an Olympic sport, or cigarettes smoked in a day. We can click to see that sex or gender at birth is nominal. Neither category is more important than the other, nor do they differ in magnitude. Length in centimeters is a continuous measurement with infinite values between the larger centimeter indicators. The winners in an Olympic sport are ranked and therefore are ordinal categories of first, second, and third place. And the number of cigarettes smoked in a day is a discrete measurement or count data. We may also reduce the detail of measurement when it makes sense for us to do so. Typically, we do this in order to create more meaningful explanations of the data. We might reduce age in years into age categories in order to analyze whether children are meeting specific recommendations for their age group. It might be useful to convert the number of times a child drank milk in a week into clinically meaningful categories of nutrients consumed, or the number of days someone exercised in a month into clinically meaningful categories of exercise. We might also take discrete or ordinal data and sometimes continuous data and reduce it into fewer categories or dichotomize the data into only two categories. For instance, we might categorize a person as a smoker or a non-smoker using their discrete count of cigarettes smoked in a day. Or we may reduce the level of education from 8 categories into whether the person has less than a completed secondary education or has completed secondary school or more. All of this is very specific to the work that you are doing and to what is meaningful to you in your field and in your data. We use descriptive statistics to summarize our data and to help us understand our data and our sample population. We may want to know, what are the limits of a variable? How many people have a certain value? What's the average of some measure in our sample? The statistics that we use to summarize and describe data differ by data type. We'll go over each of these with examples, and in topic 7.5, you'll see how to best visualize each type of summary statistic. A frequency distribution summarizes a categorical variable by displaying the values a variable can take and the number and proportion of persons or records with each value. This is typically calculated as the frequencies or counts of each value or category, and the relative frequencies or proportions of the total variable that each category contributes. We often see cumulative frequencies reported as well. The measures are the same for nominal and ordinal data, but we may take different approaches to how we display each, both in tables and graphically. For example, let's take the set of 19 total numbers. We can say they represent scores on some measure. To construct a frequency distribution that displays these data, first, we list all the values that the variable can take from the lowest possible value to the highest. We've done that here. Then, for each value, record the number of people who had the value. That's our frequency for each value. Divide the frequency by the total number, 19, to get the relative frequency or percent. So if the number 1 appears 3 times, it has a frequency of 3 and a relative frequency or percent of the total of 15.8%. Frequency distributions provide an organized picture of the data and allow us to see how each category is distributed. Are the values concentrated in one area? Are they spread out across the entire nominal or ordinal scale? There are several tools that can be used to present categorical data. Most often we use frequency tables and bar charts for nominal and ordinal data. Frequency tables display the frequency or number of observation in each category of a variable, which is usually represented by n, and the relative frequency of each category, which is the number of observations in each category, divided by the total number of observations, usually represented by a percent symbol. Contingency tables are frequency tables that display 2 or more variables at once, contingent on one another. Observations are split into levels or categories of variables and displayed in matrix cells. You may be familiar with the terms crosstabs or 2x2 tables. These are other terms for contingency tables. They can be of any row by column size, but in basic descriptive statistics, these may only display the frequencies without any hypothesis testing. I'll show you examples of each of these next. Graphical representation of categorical data can be done in many ways, including bar charts and pie charts and mosaic plots, but we'll take a closer look at these visualizations in topic 7.5. Running frequency measures and creating a frequency table in Stata is very easy to do. We use the tabulate command, which can be written as tabulate or the shortened tab. We simply type tab and the variable name and run the command. Here is an example of frequency table run on the variable HL4 in the mixed data set, which is the variable for sex. You could type the syntax in yourself or use the syntax in the do file for topic 7.3. The table shows the levels of the categorical variable in the first column, here male and female, and the second column contains the frequencies or counts of each level of the variable in our data and the total number of observations for this variable. Here we see there are 621 males and 560 females in the data. The third column displays the relative frequencies or percents, and the cumulative relative frequencies are in the last column. The cumulative frequency is the sum of percents of the current and previous categories in the table, and these always equal to 100% for the last category. So what does this tell us about our data? We know there are more males than females in the data set, but that's about all we can tell from this table. Creating frequency tables is the same in Stata for nominal or ordinal variables, but you may need to be thoughtful about the order. This is a frequency table of the nominal variable HH7 in the mixed data, which is province of residence. What is the order here? Is it in descending order of province size or population? It isn't in ascending or descending order of frequencies or relative frequencies. Is it in some geographic order? I don't know. I bet this order makes sense to many of you, but as someone who is less familiar with provinces of Lao PDR, I don't understand this order. It might be helpful to note what the order is in a footnote, but it might not really make any difference. However, when writing up a table for a report or a manuscript, we usually put some kind of order on nominal variables when it makes sense. It might be alphabetical or ascending or descending order of frequencies, either in your sample or in your population, which is a way that I prefer for many variables. If you're giving a presentation, you might put the province in which you are presenting first, and then the other provinces in some order. If you did want to sort the output in descending order of frequency, you can just add the word sort after your tab command. This is just to show you a published frequency table, this one of vaccinations in the first year of life from the full mixed 2017 sample found in the Lao PDR Social Indicator Survey 2 2017 Mixed Survey Findings Report. It shows the relative frequencies only for proportion of children who are vaccinated by how their vaccination status was reported. While it doesn't have the count frequencies, we do have the total number of children in every column. Let's run a frequency table for an ordinal variable. Use the command tab with the variable cage_6, which is age in months in 6 categories. With ordinal variables, the cumulative percent can be useful, and that you can see, for example, that 37.5% of all the children in this sample are under the age of 24 months or 2 years. We don't typically use the tables we make in software programs in our final reports or manuscripts. So I've included this table just to demonstrate that when we create our tables in Word or another program, we can choose different options for displaying nominal variables. For the first variable about where participants go to when they're sick, we listed the categories in descending order of frequency so that the most common choice was listed first. The ordinal variable is obviously in order. Depending on what you're reporting, you may include your don't know or refused categories last. You can put the overall sample n or number in the table title, but if a particular variable has a smaller sample size, you can put the small n for that variable after the variable label. For example, for what is the quality of care you get there, the n is 395 versus the total n, which is 398. And finally, when you're reporting dichotomous variables, you can choose to only report one of the choices, such as the yes response for a yes-no variable, like here where we have sees a particular doctor or nurse at this regular place of care. Creating a contingency table in Stata is also very easy to do. Use the tabulate command and just list the 2 or more variables that you want to include in the table with your row variable listed first. For an example, let's run tab HL4, which is sex, and cage_6, which is age in 6 categories. You see the row category levels and column category levels, and each cell has the value of the column level for that row level. For example, there are 57 male children less than 6 years old and 47 female children less than 6 years old out of 104 children less than 6 years old. This defaults to only showing the counts, but if you want to show percentages, you can add the options row, column, or cell to the tab command to see whichever percentages you want in the table. To create a contingency table in Stata for more than 2 variables, you can use the table function, which you may need to install after searching for it in the help menu. In the mix sample, we can run table with HL4, HH6, and cage_6. When we do this, our second variable rows are shown for each level of our first variable, with our third variable as the column categories. You may need to carefully choose which variables you put where in order to make the tidiest table. This was the best configuration for these three variables. You should try running this table with the variables rearranged and see how it looks. So we have here the count of every child's age category by their sex and whether they live in an urban area or a rural area with or without a road. For example, we can see that in this data sample, there are 9 female children who are between 12 and 23 months old and live in a rural area without a road. This type of contingency table can be very useful for trying to identify smaller subgroups of a sample with certain characteristics, but it can be challenging to read. We've covered how to use frequency tables to represent categorical data, and now we'll discuss how to run summary measures on continuous data. Continuous variables, or numeric variables, are summarized using measures of central tendency and of dispersion or spread. We commonly think of mean, median, and mode, variance, and percentiles of a measure in our sample. We will also cover data summary tables that you can use with continuous data. We summarize continuous data by using measures of central tendency or central location, which are often a single value that summarizes the entire distribution. These measures include mode, median, and mean. Which measure we use for a given distribution of a variable depends largely on the shape or skewness of the distribution and the intended use of the measure. Depending on the shape of the frequency distribution, all measures of central location can be identical or different. Is this a normally distributed curve? Yes. When we have a normal distribution, the mean, median, and mode are equal. When our distributions are skewed, mean, median, and mode are not equal. When the distribution is skewed negatively or to the left, mode is going to be greater than median, which will be greater than the mean. The opposite occurs when our variable is positively skewed. Mean is greater than median, which is greater than mode. The mode is the value that occurs most often in a set of observations, or the most popular value. If we take our example set of score data and we count the frequencies of each of our values, we see that 5 is the value that occurs most often. 5 is our mode. The mode is not always unique. You can have multiple modes or no mode. If our data above had one more score of 2, it would be bimodal with a mode at 2 and a mode at 5. If everyone scored a 5, there would be no mode. It isn't always centrally located either. A mode of 5 is not anywhere near the middle of a score of 1 to 5. But you can use mode on all data types and it is completely unaffected by outliers in the data. The median is the midpoint of a set of observations that have been put in rank order. It's the data point that's exactly in the middle. We put observations in ascending or descending order and find the center or middle value. And our sample data, we can count into the middle and find our median is a score of 3. Median uses the position of each case or observation rather than its value, and it divides the distribution into halves. It is the 50th percentile of observations. We can use this measure with ordinal, interval, and continuous data, but not nominal. Why not nominal? Because the responses must have an order and nominal data are not ordered. The mean is the measure of central tendency we hear about the most, and it is the arithmetic average of all the values. It's the sum of the data values divided by the total number of observations. In our sample, the total of all the scores is 61, and dividing that by 19 observations gives us a mean of 3.21. The method is simply to find the average of all values. It uses the most information of the central measures and in most cases is not an actual data value. We can use the mean only for numeric data, and it is very sensitive to extreme values. For reference, here are the formulas for calculating the mean and for finding a median in odd or even numbers of observations. And this table can serve as a reference for which central measures you can use with each type of data or measurement. In addition to central tendency, variables have another major characteristic, and that is their variability, or a summary figure that describes the spread of observations within a distribution. Here we see in the middle values with equal means, but unequal variability. On the left, we see equal variability, but unequal means. And on the right, we see equal variability and equal means, but different shapes. The four most commonly used measures of dispersion are range, percentiles, interquartile range, and variance or standard deviation. Range is the difference between the largest or maximum and the smallest or minimum observations. In our example, the range is from 1 to 5, so it is equal to 4. Percentiles divide the observations into 100 equal parts. The pth percentile is the value that is greater than or equal to p% of the observations and are less than 100 minus p% of the observations. In other words, the 90th percentile has 90% of the observations at or below this value. The median is the 50th percentile, the maximum is the 100th percentile, and we refer to the 25th percentile as the lower quartile, with 25% of observations with values less than the 25th percentile value. The interquartile range includes approximately 1/2 of the observations in the set that lie in between the lower quartile or 25th percentile and the upper quartile or 75th percentile. It contains the middle 50% of the distribution. It depends on a relatively stable central portion and can be used when an unusual data value is present in the observations because it is less sensitive to extreme values or outliers. The standard deviation tells us the typical amount by which an observation might deviate from the mean. It is the square root of the variance. The larger the value of the standard deviation, the more the scores are spread out around the mean. It is responsive to all individual scores, so it may not be the best index of variability when distributions are highly skewed. In a normal distribution, the standard deviation can be used to estimate the percent of scores falling within a certain range, with 1 SD containing about 68% of scores, 2 SD containing 95%, and 3 SD containing about 99.7% of the scores. This graph simply shows the intervals of standard deviations on a normal curve and the proportion of scores that they each contain. This is a reference slide for you if you want to know how to derive the standard deviation. Now to get to the part you've been waiting for, creating and viewing summary measures for interval data in Stata. To do this, we use the summarize function, which is simply summarize and the variable you want to summarize. Let's try summarizing BMI in the mixed sample. You type the command summarize BMI if BMI is less than 30. What you see is the output from Stata, which gives us the name of the variable, the number of observations, the mean, the standard deviation, and the minimum and maximum values of observations for this variable. If we'd like more than just the mean and standard deviation, we add the option detail at the end of our command. When we do this, we get a table of the percentiles from 1%, 5%, 10%, 25th percentile on up. We get the 50th percentile, which is our median. We also have the 4 smallest and 4 largest values in the data set. We still have the number of observations, the sum of weighted observations if we're using a weight, and we have the mean, the standard deviation, as well as our variance and measures of skewness and kurtosis to tell us how skewed or away from normal our distribution is. For additional measures of central tendency and spread, we need to use the table function and specify which summary statistics you want reported in the table. It's an odd function, but you can find this syntax in the do file for today's topic 7.3. You type the command table with empty parentheses, and then you specify each set of statistics that you would like to run and the variable that you would like to run them on. So we have to type statistic mean of BMI, statistic standard deviation of BMI, and so on. At the end, then we type the if BMI is less than 30. And what we get is a table of summary measures for BMI. We see the mean and the standard deviation and the median and the interquartile range and range. We can transfer our summary measures into a table format along with our categorical measures, as long as we distinguish the measures of mean and standard deviation from the measures of frequency and relative frequency. And we'll show more options like this in topic 7.5. But you can see here where the sense of coherence scale at the top of table 5.7 reports on means and standard deviations and contains ranges for subscales. But the other subsections of 2-in-1 study arm, health needs and behavior, and called referral and behavior change are all frequencies and relative frequencies. If you would like to run additional summary measures on your interval data, here are a list of statistics that you could use with the table function by adding in the statistics option statistics and in parentheses the specific stat you want to use and the name of the variable you want to run it on. In summary, descriptive statistics are used to understand our sample and our population and are used to organize and summarize our data. Categorical and interval data are distinct types of quantitative data that require different summary measures. We can transform interval data to categorical data when appropriate, and frequencies, relative frequencies, and contingency tables are used to describe and display categorical data, while measures of central tendency and spread are used to describe continuous data, and some are often best represented visually, which will be covered in topic 7.5. Final thoughts. Organizing our data with descriptive statistics and creating tables to display our data is an essential step to helping us and our audiences to understand the characteristics and context of our sample and population. Investing time here will make your hypothesis testing analyses simple and easy.